Okay, our next presentation comes from University of Kentucky Center for Applied Energy Research on operational characteristics of a small-scale slurry bubble column reactor Fischer-Tropsch synthesis study by Jim Neathery, Robert Spicer, Dennis Parks, and Bertrand Davis. The speaker is Jim Neathery.
Thanks. Well, sorry for the little delay here. I guess this is the first time I've taken PowerPoint on the road. I use it quite a bit at work, but I've always had nightmares of these problems. But I think we can get it working, but it's kind of hot in here, and I'll probably take about 10 minutes so I can go back to the old tech way of doing it. What I want to talk about today is really a work in progress. It's a pilot plant study. The focus has been on Fischer-Tropsch, but I think it's applicable to any type of chemistry that you might be interested in if you're interested in a three-phase bubble column. And I'll talk about some of the small-scale challenges we face with this pilot plant and how we can get around some of those challenges. As far as the outline, I just want to talk briefly about bubble columns, and I won't go into too much detail for time about Fischer-Tropsch. We've heard a lot about it today. I'll really focus in on the small-scale limitations, and then talk about our pilot plant briefly and how we're configured currently. And then as far as results, I'll talk a little bit about gas holdup, things like that are of interest to people operating a bubble column. And something I've always been interested in is scale-up. I'm new to Fischer-Tropsch, but throughout my career I've worked with scale-up of different processes. And at our lab we have a good setup. We have a small-scale CSTR and a larger bubble column about 10 times the volume. And then as a bonus, if time permits, I'll talk about some of the catalyst attrition. We're able to do studies of attrition, which you really can't do in a CSTR. Well, bubble columns. I think most of us here probably know some of the advantages. You get very good heat transfer, so you don't have to worry about hot spots in a reactor for poisoning or centering a catalyst. And since you get good heat transfer, you have a uniform temperature profile, so that's a big advantage. No lower limit on particle size, I list here. Well, I'm referring to, say, in a fixed bed reactor, you have to worry about pressure drop. You have a very small particle size, and your pressure drop becomes excessive, and it's costly. Although, you know, the lower limit on particle size there is a practical lower limit in a bubble column because you have to filter out the catalyst from whatever product you're making. You can also do something you can't do in a fixed bed. You can withdraw the catalyst continuously. You can add catalyst to sort of get a constant activity. And lastly, but not least, it's a simple construction, rarely many moving parts, and it's typically a lower capital cost than a fixed bed reactor on a large scale. Well, with the pros come the cons. Disadvantage is that you do have to separate this catalyst. I alluded to that a minute ago, and I think that's one of the biggest challenges in at least in Fischer-Tropsch is get the product out of the catalyst. And in terms of studying this on a small scale, your physics flow physics in a bubble column for a small scale is usually more like a CSTR because you have severe wall effects and back mixing in a bubble column in a small scale. And lastly, this is, I guess, more of an industrial concern that if you have poisons present in a bubble column operation, obviously the entire bed is affected. Whereas if you have a spike of a poison in a fixed bed, you're just affecting one small layer. I was trying to click and hoping the slide would move, but it didn't work. And of course, I'll just go quickly here, but our overall chemistry we're studying here is Fischer-Tropsch, where we're making paraffins, olefins, and some others. And in this case, we're using an iron catalyst, so we have a predominant water-gas shift reaction so we can operate at a lower hydrogen to CO ratio. And I just threw a little schematic in here. I think I grabbed this. I was too lazy to draw it, so I grabbed it out of the literature or some review somewhere. And typically in a bubble column you might have several levels. You might have a catalyst level and a liquid level. In our case, the catalyst is very fine, so it's pretty much well mixed, and we don't really distinguish any kind of level as long as you have a fairly small particle size, and as long as your superficial velocity is high enough to keep everything churned up and well mixed. And of course, you have a distribution of different particle size, bubble size, depending on your construction of your reactor, how big it is, and wall effects. Well, since we are a academic institution, a research arm of an academic institution, obviously we can't have very huge pilot plants, but I would say in terms of academic arena, we're probably one of the largest bubble column reactors that can operate under pressure. I don't know of any others, but so we're very interested in looking at these wall effects and how this might affect some of our data for scale up. And another point that I've come across is that in a small scale, in a pilot plant, you're wanting to operate continuously. So the idea of continuously being able to extract wax is very important. On the smaller scale CSTRs that we operate, we do it in a sort of a batch-wise process. But as I'll explain later, it's very important, at least in the bubble column, to continuously remove it. And it can also affect your catalyst inventory in your system, which I'll elaborate on. This is a graph of another one I've picked out of the literature that is column diameter going from 100 to about 2.5 centimeters versus the superficial velocity. You can see really three different zones. One is the slugging regime, which you have very large bubbles that go rapidly up a column. We have the bottom part is a so-called homogeneous regime, which you have a kind of a mono-dispersed diameter particles that are very uniform, and then you get a kind of a mixture of both. You get large bubbles coalescing and some smaller bubbles in their wake. Most industrial units operate somewhere up in here. Since we have a 5 centimeter column, we're sort of in this window here. So if we go up in superficial velocity, we mainly go into the slugging regime, which can cause problems. Well, why does it cause problems? Well, really you're operating, the bubbles really behave differently in a bubble column. The large slugs or bubbles tend to move very rapidly up through the column. They tend to be in plug flow, so there's no back mixing of the gas. Whereas the small bubbles are in more of a well mixed mode. They kind of back mix with the liquid in the wakes of the larger bubbles. And of course the liquid is well mixed. And this is from a recent review by Krishna at the University of Amsterdam, and he gave a really good chart here, I thought, of time versus bubble rise in meters, and he's elaborated here kind of in scale of a certain bubble size, in this case a 21 millimeter bubble size and a 0.1 millimeter column, going down to a smaller 0.05 meter column. So you can see a velocity profile here. The wall effect, since the bubble's moving up, it displaces liquid, so liquid is moving behind it, so it tends to slow the bubble down in a smaller column, whereas in a larger column it has a higher velocity for a given bubble diameter. And I must say that this downward vector means it's more back mixed in the smaller diameter. So I use a little artistic license here in this drawing, but in reality you get sort of a velocity profile crudely looking like that. You've got a liquid being taken up in gas going through the center, and a heavy liquid downward component coming down, which creates a back mix. Well, I'll just get into a few details about our pilot plant, but I would mention it's originally used as a direct cold liquefaction reactor. This is a project I've been working on since about August or so, and we've been renovating and tearing apart equipment, and we are making use of a ebulated bed direct cold liquefaction reactor, and it's a little bit overbuilt. It has a 2-inch wall thickness, 2-inch diameter, so it reminds me of one of those Civil War mortars you see in the old pictures. You know, it's just a huge walled reactor, and it's about 5 centimeters diameter, it's 2 inches, and it has a length of about 1.8 meters and a total volume of about 3.7 liters. And the CSTRs we operate are 1 liter, but we typically operate with only about a third of that volume. So in reality, the bubble column is about 10 times the scale of the CSTRs that we report. And we've just added a continuous catalyst wax separation system, which I can highlight in the next graph. Mason this morning talked about the CSTR configuration. In reality, ours is the same. We have the same downstream equipment. It's just very big compared to what they operate with. We have a hot trap that stores the reactor wax, a warm trap for the waxes, and a cool trap running at about 0 degrees C for the water phase, and also some oils. What we've done different really with this reactor is we have a wax separation system consisting of a little holding vessel, and these are not really to scale. I apologize for that. I probably should do a better job on the drawing here, but we operate with a very small volume of slurry, catalyst slurry in here. We measure differential pressure so we know how much of the reactor slurry is out of the reactor at all times. Then this flows by gravity down through a dip tube to the bottom of the reactor. And likewise, the gas and the liquid is entrained in this riser tube, we call it, and back around to complete the circuit. So we call this a riser tube, and this portion here is a downcomer, and this is where we actually do the filtration. This is a photo of the reactor with a student who's about greater than 1.8 meters tall, very tall guy, and it's just basically in a heated jacket. It looks much bigger than 5 centimeters, but it's got a heating jacket, plus it's got the metal around it, so it takes a while to heat it up. We're kind of limited on our heat up rates and cool down rates, but it's fairly simple. Unfortunately, it didn't have a lot of ports in it since it's such a high pressure vessel. Up above that where I just had is the rest of the unit where we have this overhead vessel, we call it, and the hot, warm, and cool traps. And the filtration element is down here. It's not really very clear in this photograph because of all the insulation covering it. I just happen we'd be wearing the same shirt too today. I do have other shirts. And this is more of a schematic showing the flow circuit within the reactor. It is a natural recirculation. Since we're talking small scale, we want to get away from any pumps, and also we're wanting to look at this reactor for attrition studies. So we're worried about any pumps really, adversely grinding up the catalyst. But what we do here, we start this overhead receiver. We really keep a constant head of slurry on this, and it's got a certain pressure head on it. And then likewise, you might consider this like another part of a manometer where the reactor has gas and liquid in it through the riser. So really there's a pressure head difference there that drives the whole recirculation pattern. Unfortunately, the liquid velocity in the reactor is dependent upon the space velocity. As more gas you send through the system, the faster this recirculation rate. And I've just provided a little graph that we've taken off a trend chart recorder right before we put in our new computer system. But this shows the differential pressure signal while we're recirculating. So it's a bouncy signal. This bouncing signal is about plus or minus an inch in water column. The bouncing is very important to us because we are able to see if there's a blockage in the recirculation loop. And if it happens, we still get a fuzzy kind of signal, but it's much narrower. And the really the reason for this fluctuation is bubbles going through the reactor. There's also these lines are differential pressure lines are purged with argon, so there's bubbling through the purge gas through the differential pressure lines, which accounts for this noise. But the main noise here is really just the recirculation. And when we cut the recirculation off, we see that the signal goes flat, and also we see the riser and downcomer temperature start to change. So that's another good indicator. So we have several good indicators of what's going on inside the system without a window or anything. And as far as some of the design objectives of the system, we're really worried about the wax collection inside the reactor, and our objective really was to keep a constant volume that was out of the reactor, so we could always quantify how much was out of the reactor to really nail down our space velocity. And I'll go into earlier runs where this wasn't happening, and it looked like an apparent rapid deactivation. So we tried to minimize the volume of slurry outside the reactor also, so that it's less room for error. And we built this thing so we can study a wide range of filters. So that's another sort of little side project we're working on. Well, I'll get into the results now, and really I want to talk first about gas holdup, and then a little more about, I'll probably skip over the level indication control and look more into conversion comparisons between the two different reactors. Gas holdup is very important, obviously, in a bubble column, and it's difficult to measure online. You can measure through differential pressure of the entire column, and we just weren't really set to do that, so we utilized this level indicator to really tell us how much gas is being displaced in the column at different superficial velocities. And starting up, we looked at a C30 oil, that's the top curve, and we go typically up to about 20%, which really kind of matches what we see in the literature. And that's without any catalyst, just C30, or a solvent startup oil, which is about C30. Then at the conclusion of a run we did, we varied the space velocity through the reactor and superficial velocity, and we see a slightly depressed gas holdup, but that really makes sense because it's a heavier liquid and it has a higher viscosity, and so you'd expect a higher bubble rise and thus a lower gas holdup. And just looking at a performance comparison in terms of CO conversion for three different setups. The first one is a curve typically like that Mason showed earlier this morning from a CSTR, and this top one is a run that we did most recently with the improved level control, and this was an earlier run we did years ago when we tried to utilize that tube reactor for this type of setup. And we didn't really have a good handle on where the catalyst was going. We were filtering out material, but we had to pull a lot of sample out of the reactor, flowing outside the reactor to be able to filter it. So it had a lower conversion, but I think this is because we had really less catalyst in the reactor. And we looked at this in terms of activity. When activity declined, you can see that this is the top two curves lines here are the deactivation rates. They're nearly the same, about 0.013 per day, 0.014 for the bubble column and the CSTR as we run it today. And this second one is the problem here I was telling you, where we didn't really have a handle on the catalyst inventory. So we had like an apparent very rapid deactivation, but this is really just a remnant of not being in steady state. Once we had enough catalyst was operating at a lower level, and we had slurry in equals slurry out, we had really the same deactivation rate. So it just highlights some of the problems you encounter in a smaller scale pilot plant. We've looked at the same sort of thing with a high alpha catalyst, and this shows a more steep curve in terms of deactivation, because we looked at a high alpha catalyst. I made the mistake of activating at 230 instead of 270, so we're kind of blaming that on the lower activation temperature. But we still, once again, we still see about the same constant in the CSTR and the bubble column. So we felt pretty good about that. And in terms of product distribution, very similar. The alpha value here is probably not very accurate because the run time was probably not long enough. We still have a lot of startup solvent in the reactor, but the distribution is similar, although we think the bubble column tends to have a little heavier product distribution. In terms of olefins, we start to see a few differences here between the bubble column and the CSTR. The bubble column is the dark circles. It's kind of more olefinic over the range of carbon, whereas the CSTR starts to drop off. And we think a lot of this is due to more of a plug flow nature in the bubble column. And I would mention that on my graph a couple times back, I forgot to mention that the conversion is much higher for a given space velocity, which we would expect in a plug flow type system. Let's see. Next, I'll talk about some of our newest results in terms of catalyst attrition. I didn't put this in the abstract, but I thought it was pretty unique. A lot of people are looking at catalyst attrition, but they use an ASTM test. I can't remember off the top of my head what the number is for that, but it really just gives you a kind of a comparison between two catalysts. You don't have any idea really what goes on in a real reactor with this. So I thought it would be unusual to actually test one in situ. And obviously a CSTR is not a good measure of that because it's grinding up the catalyst and gives you a very high breakdown rate. But we start off with catalyst about 22 microns. It's an iron catalyst, FT catalyst, with the following operating conditions. And we took SEM images of it before it went in. So it looks like a typical spray-dried catalyst. Very uniform spherical particles. The scale here is 60 microns. So it's in the light scattering Coulter particle size analyzer, it came out 22 microns average diameter. It looks a little bigger in the SEM. So after about 5 days online, you start to see a little more breakup, smaller particles, and I believe it went down rapidly after activation. I've got a graph to show that. This is mean particle size versus the time on stream. We started off at 22 microns, but the first sample we took right after activation went down to 14 microns or so. And I'm not really sure if that's a real attrition rate from beginning to putting it in the reactor to after activation. I think it's more of a function of not being a perfect sample point. We're sampling near the top of the reactor, so there's maybe a little room for classification. Maybe the smaller particles have a higher concentration. But you can see it keeps kind of steady here for about a day or so, then kind of exponentially drops off after about 100 hours down to about 8 or 9 microns.
Did you see a drop off when you use the ASTM method?
We didn't use the ASTM method for this.
No.
This is something that we've done in the last couple of weeks, so I plan on getting set up for that. But once again, it doesn't give you a, it really is, that method is important for comparing two catalysts. It doesn't really tell you much, if you just have a single catalyst. So when we get to comparing more catalysts, I think we'll have to, try to compare that.
Is the attrition because of physical properties? I mean, physical during the recirculation, or is it because of the wax that's building up within the pores of the structure blowing apart?
At this point, we don't have any way of knowing that, but I've got, if it happens, we need to verify if that major first portion is due to the activation. Right? At this point, we don't have enough data to really make a conclusion on that. But it appears like there's a heavy drop during activation even, so there might be some chemical component to it. And this graph just shows the cumulative particle size and how it really shifts toward the smaller particles over time. This is the raw catalyst, once again, day 0, which is right after activation, and it just sort of slowly goes up toward the smaller particle size. In concluding, we really think that for small scale, that this indication we have is fairly useful for telling what goes on inside the reactor versus, for recirculation, degree of recirculation. And we've really been on the learning curve on that. So it may be not so applicable to a large-scale reactor, but at least for us in doing the test, it's very important. We also think that the bubble column, the way we're operating it with this recirculation, is more plug flow in nature. We have a very high liquid superficial velocity, which helps eliminate some of the back mixing problems. And we want to further explore this attrition rate. I think there's more room for at least a lot of industrial interest in this sort of testing. And really, it's it's not something you can do on a very large scale. It'd be expensive to do an attrition test, on a new catalyst. And I guess I'd like to end with acknowledgements. Obviously, people that write our paycheck, the Department of Energy, University of Kentucky CAR, and my coworkers, co-authors. Especially like to thank a co-op student, Mike Lundeen, the tall guy I showed in the one photograph, and Toppin and Corinna Doss helping out with the analytical work, and Ushi Graham for the SEM work. That's all.
Questions?
I guess everybody's wanting to go get a drink now. After that.
You can't get away without one question.
Yeah. Different.
So, sort of interested in the attrition issue, and you measure the particle size distribution using laser scattering?
Yeah.
Is that correct?
Yeah. It's a Coulter, I forget the model number, but it's a Coulter particle size analyzer.
So have you ever looked at results that are, in terms of whether you use a surfactant, whether you use mechanical mixing, whether you use ultrasound, doing these light scattering experiments?
We did a little bit of that, and it turned out we didn't use a surfactant. We used we didn't think we even had to use the ultrasound blast. We were concerned about what medium we used. We turned out we use a water acetone mix, which seemed to work the best. We were worried about it being kind of hydrophobic, and since it has some residual wax, we take it out and we extract it for a couple of days and orthoxylene, warm up orthoxylene. So, but we're still you never really get all the wax out of the pores, but it seems to express pretty well.
If your results are imply at least consequence of the measuring technique.
Well, if we were ultrasonically blasting it real heavy, I think that we might have to look at that, but I think in combination with the SEM photographs, it seems to be at least in the same order. So we go.
You said you weren't sure about that because where you took the sample.
True, but I mean in terms of the raw particle, looking at the raw catalyst, it looked to be about 22 microns. You average in all the big particles, although it is kind of deceiving. It's hard to. But it's, we thought it was a pretty good eyeball guesstimate. It was in the 20s.
Because you can't get fooled. You use
Oh, yeah.
the light scanner.
Yeah.
Can you tell something about filtration? What temperature, pressure?
Yes,
how
I didn't
much
talk
goes
too much. We're applying for a patent, but I will just say it's using a sintered metal filter, but it's kind of unusual the way we're doing it within the reactor. So we can't say a whole lot about that yet.
How much catalyst goes through?
We're able to at least get in the range of the CSTR, which is less than 0.1%. We still need to do some work on it, but the CSTRs that we have do about the same.
Let us